Okay, so in general, we can now say that y of t is the same as the integral taking on values from negative infinity to positive infinity s tau delta t minus tau d tau. Okay, this is in the continuous time domain. While in the discrete time domain, we now have the sigma k taking on values from negative infinity to positive infinity. S of k vector n minus k. Okay, and here you see that s of t is a scaled parameter, the same way s of k is a scaled parameter, and delta t minus tau is the shifted parameter, and delta n minus
Sorry,
k.
sir. That y of n of the summation negative infinity to positive infinity. That's the discrete version, right?
This, yeah, this is discrete. Yeah,
Yes.
yeah,
All
this is
right.
the discrete time signal, while this is the continuous time signal. Okay. So the same way, what we are trying to say now is that once the Dirac delta function goes into an LTI system, what we get is the impulse response, right? For the continuous time. So the same goes for the discrete time. If it goes into the LTI system, so what we get is h of n, right? Okay. So the idea is that once the impulse response is known, that is h of t or h of n, once we are able to determine that, then the system response of any input can be evaluated by convolution. Okay, so that's the point. So the idea is, well, this is an LTI system. I will feed it with this input, probably an image input or an image file or a video file or a voice file or data file. Okay, so how are we going to be able to evaluate the output of that system? So we're trying to say, well, if we can tell the impulse response of that system, then we should be able to evaluate the output relative to that input using convolution. Okay? So having this, then if S of t is fed into an LTI system such that we get y of t, then it means that y of t is the same as S of t convolved with h of t.
Sorry, sir. Please, can
Yeah?
you go over I said, can you go over this part, the part where you talked about the part you talked about before you started talking about. I didn't really get what you said, understand what you said there.
The part before which of the statements? Before
Like
this?
after the top one.
This?
Yes, this part, yes, when you're explaining how you can have an idea of the output from the
Okay.
convoluted stuff.
Okay. Okay. So that's this now. This follows directly from my last statement. Now we're saying that the input, the response of an LTI system is h of t if the input is an impulse, right? We mentioned that in our last class. So once we have this impulse fed into a system and the output therefore gives us the impulse response, then we say it is an LTI system. Okay? So we're not saying that if we are able to tell the impulse response of an LTI system, h of t, that is, we have this system, it's an LTI system. If we're able to tell h of t of this system, so once we feed this system with an input, we should be able to use convolution to figure out the output, which is this. Is that clear?
Yes, sir.
Mhm.
So you're saying that once we figure out what H of T is,
Mhm.
once we feed any input into an LTI system, we can
Mhm.
always know what the output will be.
By using convolution,
Okay.
okay, such that y of t will now be s of t convolved with h of t. Is that clear?
Yes, sir.
Yeah, okay. So this is where the interesting analysis comes in, okay? So we can now pull up, okay, go ahead, please. I can see one hand up.
Yes, sir. Thank you very much, sir.
Okay.
So I just wanted to confirm what you said. Are you saying that for the first one where we fed into the system the unit impulse, that anytime we feed in a unit impulse into a system and get an impulse response, then that confirms it's an LTI system?
Absolutely.
Thank you, sir.
Okay. And once we confirm it is an LTI system, whatsoever input we now feed into that system can be derived using convolution. Is that clear?
Yes, sir.
Good. So, so if we take this system once again, that's S of t fed into an LTI system. Oh, sorry. Into an LTI system. And then we get y of t. Then it means that y of t can be derived through the convolution process. That is, S of t convolve with h of t, such that the LTI system is characterized by h of t. Now, the same thing goes for the discrete time system. When this is fed into an LTI system, so we get y of n, such that this is h of n. Then y of n can be derived by evaluating S of n convolve with h of n. And we already know that the convolution process is simply a sum of the signal spread over the duration of that signal. That is, we are taking the scale parameter multiplied by the time shifted component. So once we add that up, then we have the signal such that y of t can now be written mathematically as the negative integral taking on limits from negative infinity to positive infinity, s of tau, which is the scale component, h of t minus tau, d tau. And in the discrete sense, we now have y of n sigma being the sum of the scaled and shifted component, for which k takes on value from negative infinity to positive infinity. So we have s of k, then h of n minus k. Okay. So now I really need you to keep this information, reserve this information in some precious place in your heart, okay? That convolution produces an output that is the sum of the scaled and shifted impulses or impulse response, okay? Convolution, let's change the color.
Sir, come again.
Convolution produces an output that is the sum of the scaled, and shifted shifted impulse responses. Okay, this is very important, okay, because this is what convolution means. Okay, and when you are given, say, a signal, or better still, this expression, how do you derive this mathematically? Okay, so looking at this, is this signal shifting to the right or to the left? So we're about to find out. Okay, so let us look at the required steps. Okay, so when we want to perform convolution, what are the required steps? So we have y of t is the same as s of t convolve with h of t. And we know that this is the same as the integral negative infinity to positive infinity s of tau h of t minus tau d tau. So the first thing we want to do is that the impulse response is time reversed. Okay, now we have in this system s of t is fed into the LTI system, and we get y of t. So we can now say, well, s of tau being the same as s of t, and y of tau being the same as that. So here we have h of t, right? So we now say, well, this is h of tau. Okay. So the first thing we want to do is to estimate the time reversal of the impulse response. Okay. Evaluate the time reversal of the impulse response. So it means that of the impulse response h of tau, right? So that will give us h of negative tau, right? So it is reflected about the time scale. Okay. So once that is done, we will now do time shifting. Okay. So the next point will be to perform time shifting on this time reversed component. So what's going to happen if we perform time shifting? So here we are now going to have h of negative tau minus t, right? You know, we already performed time reversal. So we are performing time shifting on tau. Okay, so it means that this negative sign is not going to impact on that complete time reverse component. So I need you to take note of this, okay? So what will this give us? So this is now going to give us h of negative tau plus t. And this is now going to give us h of t minus tau. That is how we came up with this. Okay? So it is supposed to be h of negative tau plus t. So that when you now, if we have to draw the signal on a scale, you will realize that this signal is typical of time advance rather than time delay. So if you recall, the signal is going to shift to the left, not to the right. Does that make sense?
No, sir.
Alright, so this signal is shifting to the left. Is it because it's advanced now? Does that mean like the
Positive.
signal is being pushed, like it's being
No.
pushed?
It's been what?
Like, so I'm trying to remember the graph that you sent to us. There was one that you had like present, past, and
Okay.
past, and future.
Okay,
So
so
if it's shifting to the left, that means the entire graph is basically like being pushed like towards the past. Is that it?
So if it is positive, we shift to the right. If it is negative, we shift. If it is positive, we shift to the left. If it is negative, we shift to the right. Okay. Okay, someone said this is not clear. I can see one hand up. Victor, go ahead, please, before I go over this again.
So my question is, initially, you have to do a time delay shifting. When you are subtracting t to tau, it must be time delay. You can't do time advanced.
No. We are doing time delay. We are trying to model a practical system, a real-time practical system, not a storage device.
Oh, okay, sir.
Yeah, we are modeling a real-time practical system. So we are modeling time delay, right? But don't forget that we already evaluated time reversal. So there's a negative component here. Okay. And now this negative component impacts on this time component. So if we now perform time shifting on this component, so we are going to exclude the negative sign coming from the time reversal, which is going to impact on the cumulative effect of the time shifting. So that's why you see that we did not present h of negative tau minus t. Now, this will not be typical of the time shifting of this component, but rather is in brackets, so that this negative sign have an impact on the entire time shifting process. So when we open this up, it is now negative times this, negative times negative, positive t, okay? So where is now negative tau plus t? Is that okay? Is that clear?
Yes, sir.
Yes, sir. Sorry. Does this mean it's going to lead to a left shift?
To what?
A left shift.
Well,
on the-
we're going to see an example to clarify your question.
Okay, sir.
So I can see Dejo. Go ahead, please.
Okay, so I wanted to ask what it will be asked because you said something like right shifting, and
Don't
since you
worry.
said we're doing on T, from here it looks like we're right shifting rather than we're shifting rather than left. What you said.
Yeah, exactly. So we're going to get that cleared up. Don't worry. We'll get that cleared up. But what I needed to figure out right now is that first we evaluate time reversal, then after time reversal, we now perform time shifting. So once that is done, we now multiply the signal by the time shifted impulse. Okay. So the next step will be to multiply the signal by the time shifted impulse response, right? So once we do that, so we are going to get S of tau times H of t minus tau. So this is going to produce a single output, okay? And then we could repeat.
Sorry, sir.
Yeah?
Sorry, sir. The signal x of tau, you are multiplying it by the time shifted, what do you call it, impulse response, which was t minus tau, right?
Which is H of t minus tau.
H of t minus tau, yeah. Okay, I've seen it.
So sorry, the single output is for that particular point in time too, yeah?
Yeah, so this is a single output. at that time instant. So we're now going to repeat. So the fourth point now will be to repeat steps 1, 2, 3 over the entire duration of the signal, so as to get the limit between negative infinity to positive infinity, and then we get this outcome of the convolution. So this is the step to deriving the convolution. Okay, go ahead, please.
I would like to ask based on step 2. Is there like a principle guiding the time shifting? Because I was assuming T to be greater than tau from our starting point.
You were thinking that T should be what?
Greater than tau from
Less
the origin.
than tau.
Greater than tau from the origin.
Okay, T should be less than tau.
I mean, like
What?
is there a principle guiding the time shifting? Like,
What kind of principle are you talking about?
from step 1, we had convolution of minus tau. Then
No,
step
we are
2,
not convolution. We evaluated time reversal in step 1. Okay, it's not convolution, please. So this is a strategy for evaluating the convolution. So the first thing was to evaluate time reversal. So once you perform time reversal, the next thing would be to perform time shifting. So after performing time shifting, you now multiply the signal by the time shifted impulse response. And when you do that, you're going to get a single signal output at that instant of time. So you want to repeat this entire process for the entire duration of the signal, so as to get the total output. Well, we'll look at it. We'll look through an example, then I think things should get clearer. Okay, so Opara Wilson, please tell us.
Okay, sorry, sir. Like, I'm just trying to like clarify because it's kind of like somehow in my head. I just want to make sure that what's in my head is also what is going on here.
Okay,
So,
go ahead.
H of tau is the what is called is the impulse response, right?
Mm-hmm.
And then X of tau is the signal that we are trying to perform convolution on.
Mm-hmm.
Okay, so this is just the process by which this convolution is now achieved.
Mathematically, yes.
Mathematically. And all this is like kind of being done in an LTI system.
Absolutely.
Okay, thank you, sir. That's all.
You are welcome. Okay. So now let's look up an example which you already have in your slides. Okay. So let's assume S of t is given as a unit step function. And then H of t, okay, let's draw the system. So we have an LTI system, okay, which is described as H of t being the same as epsilon minus AT U of t. This is the LTI system. And then the input is U of t. So we have to figure out the output. Okay? So we know that S of t is equal to this, right? And H of t is equal to this. And by convolution, Y of t is the same as S of t convolved with H of t, isn't it? And this is the same as taking on values from the integral, taking on values from negative infinity to positive infinity, S of tau, H of t minus tau, d tau. Okay? Now, we can also represent this in this form to say S of tau is the same as U of tau, right? While H of tau is the same as epsilon minus a tau u of tau, right? Is that clear?
So
Yes, sir.
Okay, so let's draw a few lines here now. Let's break this board into different sessions so that okay. So if that is clear, the first thing to do is to perform okay, is to perform time reversal on the impulse response, right? But let us draw our signals the way they are, okay? Let's draw them. Now, okay. Now, U of tau, S of t is going to look something like this. Oh, let's wipe this. Let me use straight lines. So we have something like this. We have something like this. And then this is U of tau, right? So this is S of tau. So this is unit value. This is 1. This is 0 at the origin. Then this is t, okay? Where S of tau is equal to U of tau. That's what we have. Now, we see that this exponential curve is multiplied by U of tau. So multiplied by something like this, so it means that the growth in the negative infinity to 0 will be taken care of because multiplied by 0. So the only part that will exist is the part between 0 to positive t, right? So let us draw what we have here.
So I don't understand what you just said now, sir.
Don't worry, you're going to understand shortly. And I've already played with signals like this. So once we multiply this signal by U of t, so it means that we are multiplying this by this exponential curve. And this exponential curve is supposed to grow from negative infinity to positive infinity, right? But because we have multiplied by U of t, so all values before 0 will be multiplied by 0, so they will not exist. So this impulse response will only exist from 0 to some t value, right? In the positive axis, because it's multiplied by U of t. So that h of tau will look something like this, right? So the part that grew into this part have been multiplied by a unit response, okay? So it will not exist. It will be equal to 0. Is that clear? Because of this U of t component multiplying the signal. Is that clear? So this signal
Yes.
is more like saying, well, we have our time axis, so we have a signal coming this way, then we are multiplying it by this function. So between this 0 times this, we knock this off, we knock this off. So there's 1 here, 1 times this will be the same signal, 1 times this will be the same signal, 1 times this. So 1 times anything we get here will be the same signal. So that at the end of the day, all of this will be taken away, and all we'll now have is just this signal, which we have here, because U of t is multiplying the signal. Is that clear?
Yes, sir. Yes, sir.
Okay.
How do you likely plot, I mean, the illustration?
I'm struggling to
Are
hear
we
what
like
you are
getting,
saying.
I mean, like, how do you rightly get your variable since the question didn't allocate?
How do what?
How do you rightly get your variable?
How do I get my
Are
variable?
we, yes, sir, like, since the question didn't This
Well,
variable for tau.
we have not assigned any variable yet. We are just playing with what we have.
Okay, so it's just like
We have not identified the exact values, but we know it's going to take on a range of values. Now, the unit step function saturates to infinity, right? This is just growing to some infinite level. But we know it's unit step function, so the amplitude is 1 by definition. Now, the exponential function, we don't know the range it is taking to terminate, but we know that it is going to take on value from 1 as amplitude because it was multiplied by a unit step function. So this value of this impulse response cannot exceed 1 because it's 1 times that entire value. So we can tell the amplitude of our exponential function, but we don't know where it grows to in time. It grows infinitely in the time scale, okay? But we're able to identify specific values based on the definition of those signals. This unit step function and the amplitude is 1, but it saturates infinitely on the time scale. So this is just growing to some infinite dimension. We don't know where it will end. Then also, because we multiply the impulse response by some unit step function, we can tell the amplitude of the unit step function, but we cannot tell to what extent the exponential function will grow in the time scale. Is that clear?
that's not really clear.
Okay.
Thank you.
You're welcome. So now we have our h of tau. Now, let us come back to our definition. So, well, if we want to perform this convolution on this simple example, the first thing to do is to perform time reversal, right? So we are going to perform time reversal and begin to multiply everything we have here by negative. So h of tau, so let's draw this scale again. So now we are going to come up with something. Okay, no, we're now going to come up with, let's put it this way. This is time axis. So we're performing time reversal. So we are going to get h of negative tau. So it means that this signal is going to flip over this axis, and we are not going to have something like this, right? So this is also 1, right? We know the amplitude at that level. So it's now flipped to the negative time axis, right? Isn't it?
Yes, sir.
And now the next thing that that was asked is, we now have to perform time shifting on this activity. So let us perform the time shifting. So let's draw another scale here. Let's draw another scale here. And then this is T. So we have to perform time shifting. So this is h of negative. No, let's make it clearer. This is negative tau minus T, right? Which will be the same as h of negative tau plus T, isn't it? So it means that whatsoever we have here is going to shift where? Looking at this positive time. Is it shifting to the left or shifting to the right? By T.
Left.
Shifting to the left, absolutely. So let's assume this is T. So it means that this signal is going to now look something like this. So we're going to have something like this. And it will shift to the left, okay? Because we have this. Because now that we have this, so it means that we can equally represent this now. So let's change the color so that doesn't look a little clumsy. Okay, wait. So this now can also be written to be the same as h of t minus tau, right? Isn't it?
Yes, sir.
Okay.
Yes.
Okay. Now, let's change this color. So, but we recall that this is what we have here, right? Now, if this is what we have here, so this expression, h of t minus tau will now be equal to epsilon minus a into bracket. We are now representing this t minus tau u of t minus tau, right? Where this,
Yes, sir.
okay, good. Where this is 1, right? This amplitude is 1. This is what we now have. So once now we've done the shifting. So the next thing to do is to multiply this by the signal, right? So let us draw the scale again. So we now want to redraw this scale. So we already have this is shifted to this point. So we are multiplying this time shifted signal by the impulse response, right? So this is what we get, okay? Where this is 1. So this is going to be y of t. And this entire process is what we'll call y of t being the same as s of t convolved with h of t. But now, this is t, right? This is t, this is 0. And here we know that this value of t is less than 0, right? Isn't it?
Yes, sir.
The value
Yes,
of
sir.
t is less than 0. But if we try to multiply these two signals, they don't overlap in any way. So the output will definitely be 0. Isn't it? Because
Yes, sir.
S of t is not available here. S of t is only available here. Now, the time shifted impulse is only available here. So the y, now by the time we perform the multiplication of both signals, y of t will be equal to 0. So it means that at t less than 0, we do not have a value for the output. Is that clear? So now let's assume we are able to slide.
Please, can you come again?
Please come again.
Yes.
Okay. Now, I hope you understand how we got here.
Yes, sir.
Okay. Now, you see that both of them don't overlap. When we perform this operation on this particular impulse where we have to multiply the signal by u of t, we were able to chop off one part of the signal because they overlap, right? And we're able to come up with just the positive half of this signal because of the impact of this. But at this point, you see that this signal and this signal don't overlap. So if we try to multiply them at every instant of time, it will be 0, because at this point in time, s of t is 0. 0 times this is 0. 0 times this is 0. Everything here will be 0 for s of t. So y of t will be 0 at this point. Now, if we also multiply s of t by the impulse response, the impulse response values here are all zeros, right, on this positive half. So if we multiply 0 by each value of this, it will be 0. So the eventual output is equal to 0. And now this is considered as some t less than 0. Now, what if we move the impulse response into the positive plane of this time scale? So it means that t will now be evaluated at some value other than 0. What I'm trying to say is that now I want to assume that this now, t has shifted to, say, this point, for instance. So it means we are going to have something like this, right? So it means t is now greater than 0 at this point. Now, we could also shift it forward a bit to, at this point, to some other point where we'll be able to evaluate it and evaluate the value of y of t at this point, for which t is also greater than 0. Now, we can also evaluate at some other points at this point. So it means that this impulse response is sliding to some value greater than 0. So when we perform that operation, so it means that the impulse response is literally sliding over the signal. Then we will now be able to figure out a value for the output at some time t greater than 0. Okay? And then we are going to come up with something that looks like this. Let's redraw this. No, let's use black. Let's assume this is what we now have here. So this is sliding over. So this is y of t. So we are considering t, this is 0. This t-axis. So now you observe that this is at some point t greater than 0, right? And now we have our signal, s of t, and the shifted component, right? So if we now consider this, so we are considering y of t at t greater than 0 this time. So what are we going to get at this point? At this point. At this point. So we are going to get a value because they overlap. Okay, Dejo, go ahead, please. Okay.
Yes, I might be pushing you backwards a bit, but not to worry, I understand what you're saying to this point. But before you got to this point, I wanted to understand why you shifted to the left instead of to the right. I don't understand. Because from here, you said minus t, we're meant to shift t units to the right instead of to the left. I don't understand why it's
You
to
mean
the
this, right? You mean this?
Yes, sir. Yes.
Yeah. Now, we had a time reverse signal, right? You know how
Yes.
we got to this negative. But now,
Yes, yes.
we are now going to shift the time component. And when we do that, we'll have to ignore the previous negative that came about due to the time reversal.
Yes, I get.
So we did that. So once we, after performing that, that negative sign have impact on both the time reverse component and the new time shifting. So and we came to this. It is now negative tau plus t.
But we've already, because it's like you were solving, I think, one of your classes, because we already reversed it. I guess because we have reversed it. And from this, your expression, h open bracket minus open bracket tau minus t, it shows that, okay, well, what we're performing now, we're performing time shifting on a already reversed signal.
Exactly.
So therefore, we should just follow tau minus t, which is a right shifting. So
Okay.
that's why I don't understand.
Okay.
Why it was not a left shift.
Okay, yeah. Now, this signal is already existing in the negative plane.
Yes, sir.
Right? It's not existing in the negative plane. And now, we now
Yes.
have to perform shifting on that signal.
Yes.
Okay? So that value that introduced the negative shifting has impact on the shifted component. So once you resolve that mathematically, what do we get? What you are thinking to be right shifting is literally becoming left shifting, largely because that sign has changed based on the impact of the reversal. Well, it will become clearer when we solve more examples, don't worry.
Okay.
Just take
Thank
a
you,
deep
sir.
breath and you'll be fine shortly. Okay, don't worry. So now we just need to resolve this quickly. And for us to resolve this, what do? So it means that y of t will now be the same as the integral. So we're taking on values from 0 to t, okay? And this positive times this, so what we have now is just the signal epsilon minus a, t minus tau, the tau, right? This component. So once we integrate this, you know what we get, right? We're integrating with respect to tau. So we can also expand this. So that will be integral 0 to t epsilon minus a t epsilon a tau d tau, right? So this becomes a constant, right? We are integrating with respect to tau, not with respect to t. So this will give us epsilon minus a t integral 0 to t epsilon a tau d tau. And once we integrate this, so that will be
Sorry, sir. Why is that one a constant?
t. We are integrating with respect to tau, not with respect to t. And this is with respect to t. So it's a constant. So only with respect to tau is affected, isn't it? Right? Is that clear?
Yes, sir. Yes, sir.
So now we're going
No,
to.
sir. So
So
out of that U tau,
which is u tau? U tau has been taken care of. That's this. It multiplies this signal. So that's why we are now having a limit of 0 to t, right? Okay. We are supposed to have values from negative
sir.
t to positive t. But because of the u tau, which is the unit impulse response, so it knocks off the negative, so it changes our limit, and we now have 0 to t, right? Is that clear?
Yes, sir.
Okay. So now we have epsilon minus at. So once we differentiate this, a comes down, epsilon a tau, 0 to t. All right? I'm sure that's clear. So we can take on the limits. So, okay, I need to wipe this now, and I don't want to wipe this. So what do? Okay, let's wipe this part. Let's wipe this part and continue with the solution. And continue with the solution here. Okay, so once we expand this, so that is epsilon minus at over a into bracket epsilon a t minus epsilon 0, right? Which will be epsilon minus at over a epsilon at minus 1. So this will give us epsilon minus at epsilon at over a, right? Minus epsilon minus at over a, isn't it? So this again will give us 1 over a into bracket epsilon. So we can resolve this minus a plus a into bracket t minus epsilon minus at. So this will reduce to 0. So this will now be 1. So this will be 1 over a epsilon 0 minus epsilon minus at, which will be 1 over a into bracket 1 minus epsilon minus at, right? So it means that we can now define the output of this signal because at t less than 0, y of t was equal to 0. Then at t greater than 0, y of t is the same as 1 over a into bracket 1 minus epsilon minus at, right? So now we can now describe the output of this signal to look something like this. To look something like this. So say y of t is going to be 0 at t less than 0. And then it's going to be 1 over a, 1 minus epsilon minus at, say u of t at t greater than 0. So this is what we get from this convolution process. Okay, Ojo, go ahead, please. Before we run into some other basic things, then call it a day.
Okay, sir. I wanted to get understanding on something, sir. While you were doing the integration, we were integrating with respect to tau. But why is our upper limit and our lower limits t and 0 instead of tau and 0?
Now, because we are considering between 0 to t, this is the limit here.
Okay.
Because,
Okay, it's clarified.
because that is the point we shifted the impulse response to.
Okay.
And you know that impulse response is actually 1. It's a unit value, right?
Yes.
That's, it looks something like this. So we shifted this to this point t from 0. So we are integrating over that limit, right? Don't forget this t was somewhere around here before. Yeah, and we shifted it. We moved it this way. At this point, it was less than 0, right? So at this point, it is greater than 0. And that's the limit we are going to use for integration. Is that okay?
Yes,
So,
it's clear, sir.
Okay, so let us look at another.
excuse me.
Sorry, sir.
Okay, go ahead.
I'm
good. Okay, go ahead.
I would like to ask on how U of tau was eliminated. The O to T is quite clear, but how the U of tau was eliminated from the whole integral process.
Okay. Now this is the U. This value is U of, what's it called again? U of what?
U of tau.
Perfect. Now this is a unit value, right? So
yes,
once now, based on the fact that it progresses from, at this point is 0, then at this point we experience a growth and it becomes 1 all the way to infinity, saturates. Now, this signal extends this way, right? So at this point, when we multiply 0 times whatsoever value this is what? 0. 0 times this point is 0. So let's assume we have the impulse all this way, all the way, all the way, all the way. So 0 times this, at this point it is 0, right? Because this response is 0 here, is growing from 0, right? All the way. So 0 times this response is what? 0. At this point, what is it? So talk to me. Let me hear your voice. Is what? 0. 0 times this value is what? 0, right? So at this point again, it is 0 times this value. What do we get?
0 point something.
0 times anything is what?
0, definitely.
0 times this value again is what?
0.
So 0 times this value again is what?
0.
0, right? Good. Now, at this point, we have 1. Okay? Now, this is the point
Yes.
of discontinuity, and Gibbs phenomenon handles this. Okay? Now, if we now progress to this point, this value times 1 is going to give us what? This value, right? Isn't it? Anything times 1 is that value, isn't it?
Yes, sir.
So this value again, this value at this point times 1 is going to give us this value. This value times 1 will give us this value, right? This value
Yeah.
again times 1 will give us this value, so that this is the only thing that now exists here, right? So that after multiplication, what we now have is just this, and this. This is the only thing remaining now, right? So at this point, our signal is 0. 0 times 1 is what?
0.
0 times 1 again is what?
0.
So you see, everything now becomes 0 otherwise, except this point. So that's how the unit impulse response is taken care of. And then you now see that after that mathematical operation, what we have is between 0 to t. That is why instead of saying the time limit is from -t to t, so from -t to 0 is now 0. So now we're supposed to write y of t is equal to integral -t to 0, then whatsoever we have, plus integral 0 to t, plus integral t to infinity, or, yeah. Now, from t to infinity, this is equal to 0. From -t to 0, from this point to this point, is equal to 0. So the only place we now have a signal to play with is from 0 to t. So that's why we have this. And that's how the u of t is taken care of. So it cannot be shown again because it has performed this operation. Is that clear?
Yes, sir. That is in conclusion, we'll assume we'll deduce that it's just 1.
It
That
is
u of
1. It is 1. U of t is 1, but it has altered the limit of integration already.
oh,
Okay, so its
yes.
operation has altered the limit of integration. So we don't have to integrate from -infinity to +infinity anymore. We now have to only integrate from 0 to t.
All right, sir.
Okay. So, Dejo, are we clear? So that we have a lot to do? Okay.
Sorry, sir. One. Yeah, from your explanation, the explanation you gave to this, that diagram where we have the red and blue ink together, I want to understand, because what I was saying before when I first pulled out my hand was that decreasing exponential was shifted. You know, this e raised power minus it was shifted to the right at this point where the red and blue is. But before the diagram below, before you cleaned it, you said it was left shifted. I want to understand, how then did you, from the left shifting, I don't know how then you now put it such that we now have
yeah.
the right shifting
Okay.
at this other
Okay. Now, if you recall, the impulse response is more like a comb function that could spread from positive to negative infinity. And if you recall our definition for convolution, we do scaling and shifting, right?
Yes, sir.
So
Yes, sir.
after the original analysis, we realized that there was no overlap between the impulse response and the signal. So we now have to do some shifting. Okay? So as we
Some
shift,
additional.
yes. Now,
So what's the basis for that additional shifting?
that is the process of convolution. So we're going to do
Again.
yes, we're going to perform another operation that this will get clearer.
Okay, sir.
So
Thank
we'll
you, sir.
perform one more example and then it will get clearer. Okay. Okay, so now I'm going to take more questions, but I would love to quickly run through a few details. Just document your questions, okay? So I wouldn't want us to move to our next class, what we are supposed to do today. Okay, so just document your questions. I'll take them before we call it a day today, okay? Now, I want to show another example, though we won't solve anything. So we could have the convolution of two rectangles, of two rectangular pulses of equal width or duration, and the convolution of two rectangular pulses of different duration. So let's assume we have two rectangular pulses, and these are of equal duration, right? So this is 0, 1 to T1. This is 0, 2 to T2. But you observe that the amplitudes are different, A1, A2. Now, either of these could be signal and either of them could be the impulse, okay? But now we just document them as x1 of t and s2 of t. Now, if we perform the convolution of this, where t1 is the same as t2, okay, this duration, this is time, this is time. So we are saying that the pulse duration is the same. So once you perform this convolution, you are going to have a triangle as the output, okay? The output will be a triangle of this shape. Now, what if the pulse duration are different? So let's assume we have this, and then the second pulse duration is different from this. So this is x1 of t, and this is s2 of t, where this is 0, 1, t1, 0, 2 to t2. So this is t, and this is t. So here we have A1 also as the amplitude and A2, which could vary, depends, regardless of the amplitude. But in this case, T1 is not the same as T2. Now, once we perform the convolution of these two operations, so we're going to get a trapezoidal waveform as the output, okay? So this is what I want you to take note of. So this is y of t is equal to s1 of t convolved with s2 of t. While this is also y of t, which is the same as s1 of t convolved with s2 of t. So when you have something like this, so when both pulse duration is equal, so we now have this such that at this point, it will be 0, 1 plus 0, 2, which is 0. Then this pulse duration from this point to this point will be the same as t, okay? It's t. This is equal to t because they are equal. Then this other point will be the same as t1 plus t2, which will be twice t, right? And then the amplitude will be the same as A1 times A2 times t, okay? So that will give us the amplitude value. Okay, that's how you evaluate this. Now, when the pulse duration are not the same, they are unequal. So in this case, T1 is less than T2, okay? So it means that, fine, at this point, we have 0, 1 plus 0, 2. So that's the origin. 0 plus 0 is 0. So that's this origin. Now, you see that we have this point. We also have this point. So at this point, we are going to use the lesser value, T1. Why at this point, from this point to this point, it will be T2, okay? Then why at this point, it will be T1 plus T2, okay? Now, this particular point, the amplitude level will be the same as A1 times A2 times the smaller duration, T1. Okay, so this is how you evaluate signals of this format. So when you have two waveforms, rectangular waveforms, especially this is strictly for rectangular waveforms. So you look around and you check, you observe, try to observe the pulse duration. Peradventure, the pulse duration are equal. Then know that the convolution of both signals will give you a triangle. And if the pulse duration are unequal, then it's going to give you a trapezoid or a trapezoidal function. And I'll quickly run through the basic properties of convolution, okay? Properties of convolution. So, well, they obey, number one, the associativity property, such that if we have S of t convolve with H1 of t, for instance, all convolving with another H2 of t, probably we have two systems. Then this is going to be the same as saying S of t convolving with the convolution operation acting on both systems. So this is associativity. Then we also have the distributive.
Sorry, sir, I didn't get that.
Distributive property. Okay, I'll come again, don't worry. So now you see that here we have a system. So say for instance, S of t is fed into one system, which is H1 of t, and then that output is fed into another system, H2 of t, right? Then before we get the output. So it's either I perform the operation on these two to get this, alternatively, I can perform the operation on these two and then find the convolution with this. Whichever way, I'm going to get the same answer. That's associativity property. Is that clear? Is that clear? Oh, it's not talking again.
No, sir, it's not clear
Yes, sir.
for me.
I mean, I didn't understand the associative property.
Okay, so I'll take it again. So let's assume for the associativity, we have S of t. It's fed into system one. And then we now have, it's a cascaded system, for instance. So this is H1 of t, and this is H2 of t. And we need to find this. Now, we can decide to investigate the convolution process between this, and whatsoever the outcome is, we now find the convolution with this. So it will be these two convolving first, and then the outcome will convolve with this system. That's what we have here. Okay? Now, you observe that the response is going to be the same if, for instance, we figure out the convolution between the two systems first, and then that operation is now being convolved with the input. Okay? So you see, this is done first, and then convolve with this, or better still, these two done, then convolve with this. Whichever way, we are going to get the same answer because it's a linear system. Is that okay? So the order of arrangement is immaterial. We are going to get the same response.
So, sir, what you mean is that if we is like the order, like the order of the multiplication of the or rather of the convolution does not matter.
No. We are not multiplying in the time domain. Multiplication.
I mean, I meant
frequency domain.
convolution, not multiplication, rather.
Okay.
Sorry.
Yeah. Okay.
I meant convolution. It's multiplication that they taught us this thing in secondary school. So that was what I meant. What I mean is that the order of the convolution does not matter. That's like you said in a cascaded system.
Yeah.
All right.
That's associativity. Okay. I hope that's clear now. So now let us look up the distributivity. For the distributivity, we say that S of t convolve with the sum S1 of t plus H2 of t is going to be the same as S of t convolved with H1 of t plus S of t convolved with H2 of t. Okay? And then we have the commutative property such that S of t convolved with H of t is the same as H of t convolved with S of t. Okay? So there are some systems where you see H of t is convolving with the time-shifted version of the signal. Is the same thing that you get. Okay? You know, the time shifting is performed on the impulse response in our definition. But should the time shifting be performed on the signal multiplied by the impulse response, we'll still get the same thing. That's what we are saying. Okay? Then linearity. So convolution is a linear operator, okay? Just like I said, convolution is a linear operator such that any linear operation on the input will also result in a linear operation in the output. So if we perform derivative, for instance, derivative function on the impulse response, so the output will also the derivative function will also have an impact on the output because that's a linear operation. Now, when we also observe time invariance, so we now say that any time shift of either the signal or the impulse will result in an equivalent time shift in the output. Just like I said. So far, we've seen time shifting on the impulse response. So if we should also perform time shifting on the signal, the output will also be shifted in that manner. So if we are delaying the input, the output will be delayed by the same amount of time. So that's the time invariance. So the next property, I think one of our contributors just mentioned multiplication. So let's clarify that now. It's a property also. So convolution in time is the same as multiplication in frequency. Okay, so when we have y of t being the same as s of t convolved with h of t, this is the same as saying y of s is the same as s of s, h of s. H of s. Okay. So I think this is about it. And then we can also talk of deconvolution so that it's more like the inverse of the convolution operation. Well, there's another example I was going to take, but we won't be able to do that today. I'd love you to look up the lecture notes. The previous lecture note is covered, which is an example on discrete time convolution. So I understand you guys will be going on break and we'll be resuming sometime in January, isn't it?
Yes, sir.
Yeah, so
Yes.
Okay, so our next class, our next lecture is supposed to be Boxing Day, and I want to believe it's public holiday. So, but if it's not public holiday, we'll have a lecture. But I want to believe you guys should be boxing your gifts around on Boxing.
Sir, it's public holiday, sir.
Okay, okay. So if it is, so it means that we are going to be reconverging sometime in January. When are you guys going to be resuming lectures in January?
Public holiday. I will take holiday.
Okay. When exactly will you guys be resuming lectures in January?
I think this is
6th?
13th. To be communicated to us.
Okay, well, I'm sure it's in the calendar, probably 6th of January or something thereabout. So So the Thursday after resumption, we'll be having our next lecture, okay? So now I'd love you to look up the lecture notes we already have online, where we played with an example on discrete convolution, okay? And I also mentioned a few details on deconvolution. I think I have just a minute to wrap up now, so I wouldn't want to overstretch your time. Then in our next class, God willing, we should be looking at transforms. But if you've got any query from the discrete convolution example in the videos you have online, then we'll resolve that, okay? As a way of recapping this lecture in our next class. I'm sure that's fine, right? Is that okay?
Yes, sir.
Okay,
Yes, sir.
so
Yes, sir.
for now, I want to wish you a happy new year in advance, and
sir.
you have a great day and a nice weekend and holiday.
Thank you, sir.
Thank you, sir. Same to you, sir.
Thank you, sir.
Thank you, sir.
So bye,
Same
sir.
to you, sir.
Okay.
Happy New Year, everybody.
Yeah, I wish you the same.